All right, so, okay, so today I want to continue our discussion about the kind of introducing the ideas of statistical mechanics thought about from the language of the path integral. So just by way of remembering what we did last time, just recall that we had an expression for the partition function for a statistical mechanical system in terms of the path integral. And the statement was the following, that I can calculate the partition function, which you'll remember is a function of the inverse temperature beta, by computing the propagator, which is the central object that we like to compute in path integrals, for the same starting and final state, let's call it x, evaluated at a final time of minus I beta. In other words, imaginary time minus beta, and then integrated over all states x. So in other words, if I give you some quantum system and you can calculate the amplitude k for that quantum system using the path integral, you then evaluate that propagator at negative imaginary time and integrate over all states x, and you will get the partition function for that system thought of as a finite temperature statistical mechanical system. Okay, so let's put this to work by doing an example. And the example I want to do is the harmonic oscillator, the quantum harmonic oscillator. So you'll notice that in your first set of exercises, the problem I asked you to tackle was to extend what we did for the free particle moving on a straight line to a quantum harmonic oscillator, right? And the propagator that you will derive, so the propagator for the quantum harmonic oscillator with mass m is just k of x prime t x0, as we usually write, is the square root of m omega over 2 pi I sine omega t times the exponential of I m omega over 2 sine omega t times x prime squared plus x squared times, cos omega t minus 2 x prime x. Okay, so this is the expression that you will derive in your first exercise. Now we have a prescription for how to relate this to the partition function for the finite temperature oscillator. And that is, we set x prime equal to x and we set t equal to minus I beta. So to compute z of beta, we set x prime equal to x and t equal to minus I times beta, so that we get k of x minus I beta x0 equal to square root of 2 pi sinh, hyperbolic sign that is, of beta omega and omega factor that we drag along times the exponential of minus m omega x squared over the hyperbolic sign of beta omega, all times cosh beta omega minus 1. Okay. And now we have to integrate this over x. But then we look at the integral, and the only x factor there is sitting in the exponential, and it enters quadratic in x, which means that this is just a Gaussian if you ignore all of the coshes and things floating around. This is just basically something times e to the something x minus e to the minus something x squared. Okay, so Gaussians we're very happy with computing. So let's just do the Gaussian integral and see what it comes out as. So then it follows then that z, the partition function that we're interested in, is the integral from minus infinity to infinity of k of x minus I beta x naught, which is just square root by sinh beta omega, the denominator, and the numerator, it's m omega, and the integral comes out to be square root of sinh beta omega over m omega times pi over cosh beta omega minus 1 all of that under the square root like such. And if you notice, various things cancel in this expression. The m omegas cancel, the hyperbolic signs cancel, one factor of pi cancels. And so we're left with a remarkably simple expression of just two cosh beta omega minus 1 all to the minus a half. And you can put this into a simpler form by expanding out the hyperbolic cosine in its exponentials. And the hyperbolic cosine expanded out then gives us 1 minus e to the minus beta omega in the denominator, and a e to the minus beta omega over 2 in the numerator. And to touch base with what you would expect from standard methods, where you would calculate the eigenstates of the Hamiltonian of the harmonic oscillator, and then sum over all of the energies. And you will find there that this is the sum over j equals naught through to infinity, e to the minus beta j plus a half h bar omega. And the way that these two are the same is the fact that this, what's sitting inside the sum is a geometric series, if you think about it. And you can sum the geometric series and it gives you a 1 over 1 minus e to the minus beta omega in the denominator. So that's just a geometric sum, and I've reinserted a factor of h bar through dimensional analysis. So this equality comes from recognizing that the left-hand side is a geometric series, is the result of summing a geometric series. And the h bar factor can be inserted by dimensional analysis. Any questions?
I do have a couple of them.
Yeah.
So one is that this method doesn't tell us that j should start from 0, right?
This method doesn't tell us that j should start from 0.
So
Is
we
that
could
your
have
statement?
j by 2 and j is starting from 1. And then still we would have the same series summation.
Sorry, say that again.
So instead of having j plus half,
Yeah.
if we take j by 2 and start the sum from j equals 1 to infinity, then we would still have the same summation of the geometric series, right?
No, I'm not sure what you're saying. So the e to the beta, the half factor comes from the numerator.
So that's what I'm saying, that instead of writing j plus half, let's write it j by 2 and start from j equals 1. The summation, it goes from 1 to infinity instead of 0 to infinity.
You're asking to shift the series.
So, yeah, for the moment. Let's just say that we don't know that the energy eigenvalues are j plus half h bar omega. And if we do that, then we'll still get the same summation, right?
Okay.
So this method doesn't tell us that there should be a ground state starting from 0.
No, it doesn't.
Okay. So another question is that is this just a mathematical trick, or is this actually physically true as well? That if we put time as that minus I beta and take the integration, then it gives us basically the propagator is a thermal propagator. So is it physically true as well, or is just a mathematical trick?
I don't know what you mean by physically true.
So I mean, let's just say I wanted to calculate a propagator for a free particle at a given temperature.
Yep.
Not 0 temperature. Then this is correct.
Yes.
By substitution of time as minus I beta.
Uh-huh.
And just not mathematics. Like we did this because we wanted to connect it with z of beta, right?
Yeah.
So we noticed that if we do this thing, then we recover z of beta. Now my
Mhm.
question is that substitution of time as minus I beta, does it physically hold any meaning, or is just a step because we wanted to get to z of beta?
So, I mean, philosophically, I'm not quite sure what answer will satisfy you in the sense that here's an identification. I mean, is it physical to make time imaginary? I don't know.
No, not time imaginary. Just my question is just that if I wanted to calculate a propagator at a
Yes.
finite temperature,
Yes.
is just a substitution of T as minus I beta okay, and call that it is a thermal propagator at finite temperature instead of zero temperature.
Yes, but it's actually a thermal propagator. Okay, so it's actually it's a partition function for a different system. It's not the same system.
Okay.
Okay, so it's a Euclidean system, one dimension higher. So I can start off. So I can start off with a system in. I can start off with a system in Minkowski space. Okay.
Yeah.
So let's say a d-dimensional Minkowski space. So one space dimension and d minus one time dimension. Sorry, one time dimension, d minus one space dimensions. Or in fact, let's say one time dimension and d space dimensions. Right. So I have a d plus one dimensional Lawrencium spacetime.
Okay.
Okay. And then I analytically continue the time variable, and I get this expression for the partition function.
Yeah.
That partition function is actually the partition function for a Euclidean system in d plus one Euclidean dimensions. So no time, but d plus one dimensional Euclidean space.
Okay, yeah, I get it. But then how do we connect the same thing to what we have just done?
That's basically it. I mean, that's what I just said. I mean, that is the connection. That what we have here is the partition function for a harmonic oscillator in one dimension higher, one Euclidean dimension higher. So we tend to not distinguish this because we're in some sense abusing the notation a little bit and calling this the finite temperature harmonic oscillator. I'll get to that a little bit later when we return to statistical mechanics, and I'll show you how to properly think about finite temperature field theory.
Okay, yeah. Okay, we will revisit this question there.
Okay.
And I had one last question.
Yeah.
So the propagator we wrote down for quantum harmonic oscillator, it
Yes.
seems that it's proportional to exponential of x square or minus x square.
Yes.
And it doesn't appear to be translationally invariant. Shouldn't it be translationally invariant?
So say that again. The propagator is proportional to
exponential negative some factor and then x square. So should this not be translation invariant in space?
The propagator for properly the propagator for the harmonic oscillator, not the analytically continued one, right?
Yeah, the original one.
So the original one, okay. So
yeah.
what's the question? This should be translational invariant.
Yeah.
So if I shift t and x,
yeah.
I agree it should be translation invariant. We built it that way, and it is, but it is in a non-trivial way. So you should check that.
Okay, I'll check.
Okay.
Thank you. Yeah.
In particular, the cross terms will feature in that. So it's not just the x prime and the x prime squared and the x squared, but the x prime term features in making that translation invariant.
Okay, yeah, great. Thank
Okay.
you. Yeah.
All right. Okay, so right. Let me just pick up on the point that Nitin raised now with regards to the connection between the Euclidean system and the Lawrencian system. And in fact, we can use this to give a direct integral representation for the partition function. So to unpack this a little bit, so let's write it like this. So let's note that once I start off with the propagator and I set x equal to x prime and t equal to minus I beta, I find that k of x minus I beta, x and 0 is equal to the integral from x at 0 to x at minus I beta, sorry, x at beta of the integral over paths of e to the I times the integral from 0 to minus I beta with respect to time of m x dot squared over 2 minus v of x. All right, so that's just the Lagrangian, which is the difference between the kinetic energy and the potential energy. And now the integration that I'm doing is an integral taken over the negative imaginary axis, imaginary t axis. So I've analytically continued the time variable. So this is the real part of t. Sorry. And this is the imaginary part of t. And my integral goes, sorry, let's make that a little better. My integral goes from 0 to minus I beta. Okay, so the integration now runs along the negative imaginary time axis, and we can do this integral. We can do this integral over a real time variable by analytically continuing. So now change variables to a new variable called tau, and tau is going to be I times t, so that now I can write k of x minus I beta x0 as the integral over paths xt of the exponential of minus the integral from 0 to beta now of m over 2 dx by my new time variable, my new analytically continued time variable tau squared plus v of x. All of this is integrated with respect to the new time variable tau. The integral is taken over paths x of tau such that x at naught is the same as x of beta, and both of those are x. The path variable x of tau is now a periodic variable, where x of tau and x of 2 pi beta are the same thing. And so the configuration space is effectively a circle, and the circle has radius beta over 2 pi. So this is called a thermal circle. Let's make a note of that. So the integration is done over a thermal circle, which we call S1 beta. Okay. And this is called the imaginary time or Euclidean path integral. And it's defined by associating to each path some amplitude e to the minus se, where se is a Euclidean action. Notice now that there's a relative plus sign between the kinetic term and the potential term. This is why it's called a Euclidean action. And it's obtained by the Minkowskian action by changing the sign of the potential term, basically, and changing t to tau. Okay. And this is what I meant when I said that the system at finite temperature is associated to a Euclidean system 1 dimension higher. Okay. So now I want to change track a little bit, having made a small introduction to statistical mechanics. I want to change tack a little bit and return to our quantum mechanics problem. And the quantum mechanics problem will be one of perturbation theory. And so the statement I need to make here is that very few things in physics can actually be computed exactly. And those that you can compute exactly are typically quite difficult to do already. And for everything else, we have perturbation theory. And the idea of perturbation theory is that, at least in the way that it's used in quantum mechanics, and this is also true of quantum field theory, is as follows. What we do is we solve an associated simpler problem, and then you expand, usually by some Taylor series expansion, whatever quantity of interest that you want to calculate around the simpler problem. Okay, so perturbation theory is all about finding a simpler problem that you can actually solve and then making an expansion around it. And you think about the way you learned about curves, for example, when you first encountered calculus. What you did was you found a simpler problem that you could solve. And if you wanted to calculate, if the problem you really wanted to solve was to calculate the tangent to a particular point, what you did is you found a simple problem that you could solve and you made an expansion around it. And zooming into that curve gave you a straight line. And that straight line is something that you could understand. And then you went further back and you added corrections to that straight line that gave you some quadratic approximation to the curve. You went further back, you added corrections to that until you eventually get the shape of the curve that you wanted. So this philosophy remains pretty much the same. Find a simpler problem that you can solve, make an expansion in some small parameter around that point, and that'll give you an approximation to the answer for the quantity you're trying to calculate. In order to pave the way for what we really want to do, which is to get to the idea of Feynman diagrams in quantum field theory and string theory, I want to build some intuition first. So to build some intuition for the idea of perturbation theory and not dive straight in, I want to do something much simpler. And the much simpler thing we're going to do is solve an integral. Straight up one-dimensional integral. But the philosophy of how we approximate the solution to this integral is precisely what carries through to quantum mechanics, where we will study the harmonic oscillator, as well as quantum field theory and then string theory amplitudes. Although I'm not sure we'll get to any string theory amplitudes, but certainly the quantum field theory amplitudes. Okay, so it's very, very important that you pay very close attention to this next example. It is a simple one-dimensional integral on a straight line. So nothing difficult about it in principle, but what we do here will really pave the way for what's to follow. Okay, so to pave the way, to build some intuition for perturbation theory, in quantum mechanics and quantum field theory, let's consider the following integral. I'm going to call it I, and I is very simply going to be the integral from minus infinity to infinity of e to the minus a half x squared plus lambda over 4 factorial x to the 4, like such. Now, in fact, let me write it as exponential of minus a half x squared plus lambda over 4 factorial x to the 4. So what are we doing here? Well, the first thing to note is that if lambda was 0, then we just have a Gaussian integral, and certainly we can integrate out the Gaussian integral very straightforwardly. Secondly, because we're integrating out x, so this is not an indefinite integral, it's a definite integral. We're integrating out all the x dependence. The result is that this integral I is actually a function of lambda. This is important. The third point is that for a general value of the integral of lambda, we can't actually evaluate this integral exactly. Okay, it's nothing that you can evaluate in a closed form. And so we need a better way of tackling this problem than trying to stare at it hard enough and see if we can come up with an actual solution, or even getting numerical answers. We'd like something that gives us some more intuition for what this perturbation by lambda is doing to the problem. So let's note these 3 points, because they will be important in what follows. So the first point, as I said, is that because I can integrate out all the x dependence, this integral is really a function of lambda. The second point is that for a general value of lambda, we can't, in fact, evaluate this in closed form. But when lambda is in fact equal to 0, so I at lambda equals 0 is basically just the Gaussian integral from minus infinity to infinity of e to the minus x squared over 2, which is just square root of 2 pi. So we know what this integral is for at least one value of x. Okay. Is everybody with me?
Yes.
Okay. So the question then is, how do we even approximate I of lambda for various values of lambda? Okay. So to proceed, to approximate I of lambda, I want to consider something different. And this different thing is going to be an integral, which I'm going to call a. And a is going to be a function of some variable that I'm going to call j. And my integral a is going to be the integral from minus infinity to infinity of the following exponential. It'll be the same Gaussian, so minus a half x squared plus some term that's linear in x. Okay. And j there is the coefficient of that linear term. In what's going to follow, this guy j here is going to be called, so this, sorry, let's do that again. So this is a linear perturbation on the Gaussian. So why do I even want to consider something like this? What does this buy for me, actually? See what it does for me. Let's do the following. I'm going to remember here that a is a function of j, right? And so I can treat it like any other function. This function happens to contain j in an integral, but who cares? Let's just think about it as some function. What can you do with functions? Well, one of the things you could do with functions is differentiate them. So let's try to differentiate this a with respect to j. So differentiating, we find that dA by dj is the derivative operator acting on the integral. with respect to x of e to the minus x squared over 2 plus jx. And fortunately for us, unlike Newton, when Leibniz invented integrals and derivatives in calculus, he also told us how to differentiate under an integral. It said that you can take the derivative under the integral sign as long as you make it into a partial derivative, because now it's acting on an integrand that is both a function of j and of x. So that's the derivative of the exponential minus x squared over 2 plus jx, like such. And now you recognize that the partial derivative, Now you recognize that the partial derivative pulls down a factor of x because it's just acting with respect to j. So this thing is just the integral minus infinity to infinity of x e to the minus x squared over 2 plus jx. Okay, good. But you'll also recognize then that similarly, if I went ahead and calculated the second derivative with respect to j, I will simply pull down two factors of x, e to the minus x squared over 2 plus jx, etc. Well, it's not hard to see then, just following this logic, that any function of the derivative operator acting on a of j must equal to the same function of x times the exponential x squared over 2 plus jx. Okay, so this f here is some arbitrary differentiable function that whose specific form I don't really care about. All I care about is that it's a differentiable function. So on the right-hand side, I could think of some derivative operator that says, I don't know, second derivative squared plus 3 times first derivative plus a constant. That would be a function, capital F. And the point is that applied to this function j, all that happens is that I get a prefactor in the I get a factor in the integrand of that same function, just of x. So where I said second derivative plus 3 times first derivative plus 6, I would inside the integral get x squared plus 3x plus 6. Does that make sense?
Yes.
Okay. So in many textbooks on quantum field theory, like Tony Z's Quantum Field Theory in a Nutshell, as an example, this relation here he calls fundamental relation of quantum field theory. Okay, this is absolutely crucial to everything we're going to be doing coming up. And it's so important that I'm going to stop here. I'm going to ask you to prove as your exercise and a hint for this is to use Taylor expansions. That's why I needed this function to be a differentiable function. Okay. And next time, we're going to complete this exercise by using this function, by using this relation to solve the integral, to approximate the integral I of lambda that we started off with. Okay, any questions? Good. All right, thanks everybody.